Okay, so I will share my screen. So you see my screen?
Yes.
Yes. Very good.
Okay, great. So thank you very much for inviting me to speak here. And I assume that I'm the first speaker because of the time difference. It's 9 p.m. Here in Japan. So I'm going to talk about big data, big computation and machine learning in numerical weather prediction. So I have been working on data assimilation on numerical weather prediction. So here's my brief background. So I got a bachelor's degree in 2000 from Kyoto University, and then I started working for the Japan Meteorological Agency. And then I had a chance to study at the University of Maryland. I had 2 years to do master's degree, but very fortunately, and also I worked very hard to get a PhD in 2 years. That's a record in the University of Maryland, as far as I know. And then I went back to the JMA, that's a weather service in Japan. And so what I did in my PhD was about the ensemble Kalman filter with numerical weather prediction model. And then I developed the ensemble Kalman filter system with the operational data simulation for the operational numerical weather prediction. And then I had a faculty position at the University of Maryland. And then about 7.5 years ago, about 8 years ago, I went back to Japan in Kobe, where at that time Riken had a brand new K computer that was also the world's #1 computer at that time. So I have been leading the data assimilation research at Riken for the past about 8 years. So that's about my background, and this is my team. So recently we took a picture, the group photo over Zoom, because that was the only possible way to get a picture. So we have about 10 to 15 scientists. And at this moment, we have like 13, I think it's 13 scientists, including me, working on mainly numerical weather prediction. So I'm going to first talk about our most recent work on numerical weather prediction using a big computing resource. So this is a strong motivation for us. That was a surprise. Only in 10 minutes, this river became like that. And 5 people unfortunately died from this heavy rain that occurred in the mountain region, and only in 10 minutes, the water flew into the city, and then the river became like this. And so we started this project in 2013. That's 7 years ago. And at that time, we had a new observing system that is a phase array radar shown in the bottom left. I hope that you see my pointer here. If not, let me know. And we also had a brand new, at that time, K computer. So we had an idea to combine this new sensor that produce 100 times of more data than the previous generation sensors. And also we have the powerful supercomputer that has a processing capability of orders of magnitude more than other computers. And this is what we achieved. So top left is the observation from the phase array. Every 30 seconds, we get a full volume scan. That's really amazing. And usually we cannot really simulate this type of rain, but with simulating every 30 seconds, dense and frequent observation data, we could get this very small scale convective system very precisely in the computer. So that's what we could do with the rapid update convective scale data simulation. So this movie is available on YouTube, so you could take a look if you are kind enough to click and take a look. Then that will raise the number of views. This is ranked, used to be, well, was ranked number 6. I don't know how what's the rank at this moment, but we have a Riken channel that has several thousand of contents, and this is top 10. So I hope that today about 100 people here can raise the number here, the 3rd digit. Anyway, so we had this result. That's really was a lot of work to make this work. Most recently, we aimed to test this system real time for Tokyo Olympic and Paralympic Games. Unfortunately, the games were postponed, but we did the real-time test. So this is a new radar system that's dual polarization. So that's even better than the previous one. And the phase array. So this is a new phase array. And we had this phase array radar in Saitama, that's right north of Tokyo, and covering most of the regions of Tokyo Olympic Games and Paralympic Games venues. So we use this, and also we made a special arrangement for, sorry for the Japanese web page image, but this is a supercomputing center at the University of Tokyo, and we had a special arrangement for an exclusive use of this oak forest packs. That's like 3 times of the K computer. That's a newer computer of the University of Tokyo and Tsukuba University. And we set up the domain like this, 18 kilometers, 6 and 1.5. And finally, we decided to do at 500-meter resolution. And this is a radar site, 60 kilometers radius is a range of the radar. And we have the forecasting system, 30-minute lead time, refreshed every 30 seconds because we get the data every 30 seconds. So this is quite a challenge for computations. So we need to do all the computations for every 30 seconds for data assimilation. So this shows a past event, some test case. The left is the JMA, operational nowcasting. So numerical weather prediction doesn't really work at this scale. So the nowcasting system is the only available system that can predict this type of event. So this is a 10-minute lead forecast. And this is the actual observation. So we have a heavy rain here that develops within like the order of minutes. So in 5 minutes, it changed quite a lot. So that's why 10 minutes prediction cannot really predict this rapid development of this heavy rain here. But our system could predict this rapid development because the numerical weather prediction model is a process driven, so that will develop the convection within the model. So the process driven model predicts rapid changes of rains. And the nowcasting is basically just optical flow, cannot predict this rapid change. So it can predict the motion, but it cannot basically predict the development or weakening of the rain system. So that's the advantage of having a numerical weather prediction system, even at this scale. So we have a smartphone app so that many people can easily access to the prediction data real time. So every 30 seconds, we have up to 30 minutes prediction. And this is a past case so that we can predict. So the initial time was 0:30. So this is 5-minute lead and 10 minutes lead forecast. And this is really a heavy rain, more than 80 millimeters per hour. So that's really heavy rain, and we could predict this very small scale heavy rain. So this is the actual real-time test in August. the beginning of August that we did. And this shows the forecast lead time, so that the processing time, the computing time, and also the data processing time is about 3 minutes to produce 30 minutes forecast. Then we do the data simulation every 30 seconds, and we run an extended forecast up to 30 minutes. And that takes a few more minutes, so that the processing time takes about 3 minutes. So most of the time, we get the 30 minutes forecast ready in about 3 minutes after observation time. So we receive the observation within 10 seconds after the observation. And then this is a processing time, about 2.5 minutes, so that we produce, so this is a processing time and histogram. So most of the cases, out of more than 10,000 prediction cases, most of the cases we get the prediction in 3 minutes. So that's very good. So what we did is data simulation, because this is the first talk I will briefly talk about what is data simulation. I assume that most of you are already familiar with this. The data simulation is like this plus sign here to combine the observations with the simulations. And the simulations is process driven and deductive and within the cyber world. And the observations are basically data driven and inductive from the real world. So we have a general workflow data simulation. So we have an initial state in the computer, and then the computer computes, and then we get the future state. That's a simulated state. And then we get the observations. And this black box combines the simulated state and the observations to produce the next initial state. This is a feedback, so that we have a feedback loop. That's why we get a beta estimate. So how do we produce the process-driven model? That's based on our knowledge or analysis of the data. So we first observe the nature, and then we understand the process of the nature process. And then we come up with an equations or the physical law, and then we derive the algorithm that we can compute in a computer, electronic computer at this time. That's how we do science. And here's what we do in data simulation. So we need to compare with the simulation with the observations. And the observed variables are not necessarily the same as the simulated variables. So that's why we need to convert the simulation to the observation. Then we can take the difference. So this difference can help to find out the best estimate at this time to combine. Okay, how we can combine these two information. So the data simulation is basically the mathematics of the errors. So we have the uncertainty of the forecast, like ranging like this, and the uncertainties of the observations. And then the data simulation combines these two independent information. What we do is a Bayesian estimation. So if we have the prediction data that has this probability, like this shape, and if you have the observation in the same space with this probability density, and then we multiply these two probability density, and then we normalize so that we have a probability action, so that the integral of this function should be 1. And then we get this steep function that's a best estimate using both forecast and the observation. So that's what we basically do in data simulation. So the probability distribution is really essential in data simulation. Again, data simulation is the mathematics of the errors. So to represent the errors, what we usually do is to run an ensemble forecasting. Each ensemble member represents the random samples from the distribution. So this is a case when we tested with a K computer, 10,240 ensemble Kalman filter using 10,240 ensemble members. This is like 2 orders of magnitude bigger than the what you usually done in the Earth in numerical weather prediction. So we usually run like 100 ensemble members to represent the distribution. Just a curiosity, we run, because of the large computer, we decided to run this 10,240 ensemble members. So we can plot the histogram using 10,240 like this. This is a single variable at single grid point. This is a humidity variable. We have 3 peaks, but if we reduce, well, we take the subsamples of this 10,240, then we usually run like 80 or 160. That's a normal choice. We cannot really represent this, this shape. And the Gaussian assumption may not be necessarily a good assumption for this variable. And if you look at the Kullback-Leibler divergence from the Gaussian distribution, this is some variable of this model. With 10,240, we have some non-Gaussian structure at these spots. But with 20 members, we have a lot of sampling errors, even 80 or 160. We still have a lot of sampling errors. So to represent the non-Gaussian structure, the distribution, we need at least 1,000 ensemble members. Otherwise, we have a lot of contaminations by the sampling error. So having 10,240 ensemble members, comparing 80 members, we can improve the forecast. This is an idealized experiment, but if you run the ensemble Kalman filter at different ensemble size, this black is 80 members, and red is 10,000 members. And this is the error, so the larger, the worse. And this is 1-day forecast error for 80 members is equal to 5-day forecast error of 10,000 ensemble members. We use exactly the same model with the same observations. So just having more ensemble members could potentially help improve the numerical weather prediction. So what we explored using the K computer was to combine the big data with big simulations. So we pushed the limits of what that we usually do. So 2 orders of magnitude more than what we do in the regular problems. So this is 10,000 ensemble members that I showed, and also 30-second update is 120 times faster than hourly update. Hourly update is already fast, but 30-second is 120 times faster. And 100-meter mesh, that's usually 10 times, 100 times more grid points than 1-kilometer mesh to explore the future system. So now we have Fugaku, that's ranked #1 at this moment. And the unique characteristic of this Fugaku, this is good for both machine learning and big data assimilation. So usually the K computer, including the K computer and most other high performance computers, are not suitable for machine learning because well, it's not necessarily true, but K computer was mostly CPU-based computer. And the machine learning is not very efficient with the CPUs. But the Fugaku has new architecture, so that this is good for the half precision, for example, half precision computations that's usually used for the machine learning, and also very powerful for the normal big computations. So at first we were planning to have just a good computer for big data assimilation. So we planned to run a global 3.5-kilometer mesh, 1,000 ensemble members. So what we did, I showed that the global 112-kilometer mesh, that's a lot coarser resolution, but we explored the extreme of a large sample size to represent the distribution. So Fugaku has, roughly speaking, 100 times more computational power compared with the K. So that if we increase the resolution like this, then the mesh size is 32 times more. So in terms of the grid points, it's 1,000 times more. So 100 times computational power is not good enough to afford this 10,000 ensemble members. That's why we reduced the sample size by 0.1. So we successfully run this system, and I think that we will show this result in the supercomputing conference in November. So if you're interested, the supercomputing conference, we will present what we got in this 3.5 kilometer mesh, 1,000 ensemble members. So, but the thing is that we can, so Fugaku is also good for the machine learning. So this is what I showed about the data assimilation workflow. And we were thinking to merge, to converge the DA and the machine learning, or the artificial intelligence techniques. So the thing is that we have a lot of learning data produced by the high resolution or large ensemble big simulation. So those data are too big so that we cannot move around. And so the idea is that we run this big simulation and we use that data, the big data that we cannot move around, for learning, machine learning, so that if we can run the machine learning algorithms on the same HPC, then we don't need to move the data. So the Fugaku is capable of doing that. So we have a number of ideas to improve data assimilation using the machine learning algorithms. And this is one example. So we explored to improve the nowcasting method, because we could do every 30-second update, numerical weather prediction in 3 minutes computational time for 30 minutes prediction. But that required a large supercomputing system that is very unique. So even if we develop that kind of system, not many people can run that kind of system. So to make it available for, well, to make it more available, we need to improve the computational efficiency. So that's why we explored one method based on nowcasting technique, but not the traditional optical flow type of nowcasting, but the data-driven type of deep learning algorithm. So this is a case of convolutional long short-term memory algorithm that was applied by a previous study by Shi et al. For the 2-dimensional radar image, but we have 3-dimensional dense radar image every 30 seconds. So that we apply the method, extended the method to 3-dimensional data. So we push the past observation time series, 3-dimensional image. Then we have multiple layers of the convolutional LSTM to produce the future image. So we have training data of this observation data. But this algorithm can take the future image, but we have no future image in the real time. So at this moment, we have no input of the future data. This method works well compared with the optical flow. So this is observation. Again, the decay or the rapid intensification, the change, is hard to predict using the optical flow. The optical flow is just advect the patterns. So this is observation 2.5 minutes prediction, and this is dropping precipitation. That's why it decays quickly. But the optical flow cannot predict this decay, but the LSTM can predict very well. So that the PET pattern is much similar with the LSTM. So the LSTM is effective. So we have the numerical weather prediction system as a future image, or the optical flow system as a future image, so that it can potentially improve the prediction. So that's how we could improve the current system with the LSTM. So this is a threat score. This is just a preliminary result. showing the comparison of the threat score. So higher the better. Yeah. This is the different threshold of the threat score. So this is a heavier range. And the red seems to be better than the others. And the red is the LSTM plus the numerical weather prediction. And this dashed curve like here is the LSTM plus the optical flow algorithm. And pure LSTM is green. So we have slight improvement using the numerical weather prediction system. So we are hoping that we can get the better result, but still work in progress. And another thing that we are exploring is to accelerate the model prediction, this simulation part using the surrogate model. So we have a high resolution model that is expensive. But we could replace this high resolution model by the convolutional neural network. So this is a purely data-driven statistical model replacing this high resolution physical model. This is process-driven. But this is very difficult for the complex model. So that we tested this idea to run a low resolution model. This is the hybrid approach. So we run a cheaper low resolution physical based model, and then we get a low resolution prediction field, and then we use a convolutional neural network to fill in the gap with the high resolution. We use so this is a proof of concept study. So we use a Cauchy-Jostrophic model at 2 different resolutions. So this is a high resolution image of the potential vorticity field. And this is a low resolution image, basically the same time. We have the high resolution model. This is considered as the best result. And then we compare with the convolutional neural network. This is a surrogate model. And this is a low resolution physical model with convolutional neural network filling the high resolution component. And this is the linear interpolation based on the low resolution model. So this basically has a low resolution components, no high resolution components. So if we compare the prediction accuracy, compare with the high resolution model, the green, so this is a mean absolute error. So the error lower the better. So this green is a hybrid approach, and the linear interpolation is blue, and the convolutional neural network is red. So even for this Cauchy-Jostrophic model, that's supposed to be a simpler version of the numerical weather prediction model. The convolutional neural network has a difficulty predict, so that the error grows really quickly. But if we run the low resolution version of the model, then that will improve quite a bit, while we can save a lot of computer time. So this is the computer time for the high resolution model, and we save a lot of the computer time. Okay. We also apply the machine learning to predict the model error. So this is a very first stage of this research. So we use the Lorentz for the variable model, and we have a forecast data, and we have the observation data. So if we run the local ensemble transform gamma filter, we just have the analysis. So this is the general workflow of the data assimilation. What we added was this bias correction. So we assume that this model is not perfect. So the observation is produced with a different model. Then we need to fill in the gap due to the imperfections in the model. Then we estimated the bias using this function B, that's a recurrent neural network. And then train this network B with the set of the available data. Yeah. So we use the LSTM here again. and you use Lorentz 96, and we compare without the bias correction. And with the bias correction, we get a lot of improvement using the LSTM. This is a polynomial fit to estimate the bias in the model. So we designed different types of the bias in the model. So this is a case with shear Lorentz 96 model proposed by Manuel Pulido. In this case also we have the LSTM have lower root mean scalar compared with other methods. So this blue, this one is no correction. We have a linear correction or the fourth order polynomial. Or the LSTM did the best. Okay. Okay, I think that I will skip this part due to the time. So the idea is because we are thinking about the future direction, the computers will be capable for both the big computation and machine learning. Then we have the big data from the big computations, and we have a machine learning algorithm that can use those big data without moving around the data. So that will, I think, pioneer the new methods in meteorology. Thank you very much for your attention.
So thank you very much, Takemasa. We don't have much time for questions, but we do have some questions in the Q&A. So I don't know, Takemasa, if you're able to stay with us for a little while and perhaps answer the questions in the Q&A.
And I see one question: what feature of Fugaku make it suitable machine learning? Yeah, the Fugaku, I'm not an expert in hardware.
Would you mind, sorry, Takemasa, would you mind perhaps typing a response into
okay, yes,
then we'll move on to the next speaker. And if anyone else has questions, if you could put them in the Q&A, and hopefully Takemasa can stay with us to answer the questions.
Okay.
Okay, so thank you very much.
Thank you very much.